In order for us to do the next example I'm going to do, we need to take a look at some trigonometric ratios of special right triangles. So we're going to combine two things together. We have our special right triangles. Those are the 45-45-90 and the 30-60-90 triangles. And combining that with SOHCAHTOA and the ideas of our trigonometric ratios, we can come up with some values for some specific trig functions for a 45 or a 30 degree or a 60 degree angle. So to start with, let's take a quick look at our ratios again and just kind of remind ourselves what those look like. In a 30-60-90 triangle, there are specific ratios that we can use. If we know one of our side lengths, we can calculate the other two. Our shortest leg that we have in the 30-60-90 triangle, our book has labeled with the number 1 here instead of a variable. When you go from the shortest side to the hypotenuse, it has to double. So if the shortest side has a length of 1, the hypotenuse would be 2. And when you go from the shorter leg to the longer leg, you multiply by root 3. And 1 times the square root of 3 is the square root of 3. So if you have a 30-60-90 triangle and you know that the shortest leg has a length of 1, then the hypotenuse has a length of 2, and the longer leg has a length of square root of 3. Let's say that instead of 1, you had a different number. Those ratios would still be in place, so if this is like 4, then this side would have a length of 8, and this would be 4 times the square root of 3. When you go through and you set up fractions and you look at the ratio, it doesn't matter if you're going from 1 to 2 or from 4 to 8. The ratio of those two sides would be 1 over 2, or a half, or 4 over 8, which is also a half. And because sine, cosine, and tangent, because those are ratios, we can actually come up with a reduced ratio for the exact value of a 30 or a 60 degree angle. So, taking a look at this triangle, the sine of a 30 degree angle, that would be opposite over hypotenuse, that would be equal to 1/2. So the sine of 30 degrees is a half. Here's our right triangle, here's our 30 degree angle. I know sine is opposite over hypotenuse, so the sine of 30 degrees is a half. And it actually doesn't even matter if it's a 1 and a 2 here, you're going to get 1/2 once you simplify and reduce your final answer. So again, if this were 4 and then 8, the sine of 30 degrees would be opposite over hypotenuse, which would be 4 divided by 8, which would still give you an answer of 1/2. So it actually doesn't matter what the size of the triangle is. The sine of a 30 degree angle is always going to be equal to 1/2. And that's because those 30-60-90 triangle ratios are all similar triangles and would reduce down to the same value. Similarly, the sine of 60 degrees, so 60 degrees, now we're looking here at our angle, the opposite over the hypotenuse would be the square root of 3 over 2. So you can get the sine of a 30 degree and a 60 degree angle. The sine of a 30 degree angle is a half, the sine of a 60 degree angle is always the square root of 3 over 2. Similarly, if you did the cosine of a 30 degree angle, that would be adjacent over hypotenuse, which would be the square root of 3 over 2, or the cosine of a 60 degree angle, now looking at our 60 degree angle here, adjacent over hypotenuse would be 1/2. Similarly, we can calculate tangent of 30 and tangent of 60 degrees from there. The tangent of a 30 degree angle, that would be opposite over adjacent, which would be 1 over the square root of 3. And then you'd have to rationalize that, and you would get a final answer of the square root of 3 over 3. So, in a particular problem, if you happen to have the sine of 30 degrees, we can actually calculate and know exactly what that value is. The sine of all 30 degree angles is 1/2. The sine of all 60 degree angles is the square root of 3 over 2. And we also have values for cosine and tangent for 30 and 60 degrees as well. So in the problems that follow, you're going to have one of these values in the problem, and you'll need to plug that number in. We can do the same thing also with a 45, 45, 90 triangle. If we're taking a look at the ratios in a 45, 45, 90 triangle, we know that the two legs have the same length, and if you multiply either of those sides by the square root of 2, you'll get the hypotenuse. And it doesn't matter what numbers we choose, whether it's 1 and 1 and the square root of 2, or a different set of numbers, because the ratio will end up being the same, we'll get the same answer for all of these. So the sine of a 45-degree angle is the square root of 2 over 2. The cosine of a 45-degree angle also happens to be a square root of 2 over 2. And the tangent of a 45-degree angle, that happens to be 1. So we're going to be using those 6 exact values for a 30, 60, 90 triangle for sine, cosine, and tangent, and these 3 values that we have for the sine, cosine, and tangent of 45 degrees in the problems that follow. All right. So we're going to use that information that we just took a look at to be able to do this problem. Use a trigonometric function to find the value of x. So I have a right triangle here. Not only is it a right triangle, but I do know that it is actually a 45, 45, 90 triangle. So in this problem, I know that this is 45 degrees. And in this 45-degree angle problem, I'm going to be using that for my angle for theta. In addition to giving you a 45-degree angle, what's going to be given to you in the problem is 2 of the 3 side lengths. One of those will be given with a numeric value. In this case, I will put in the number 18 here for our hypotenuse, and then one of the other sides is going to be your value for x. Let me just put that here. So the directions say, use a trigonometric function to find the value of x. I'm going to let my acute angle here, 45 degrees, be my angle theta. And now what I want to do is take a look at these 2 values, the number 18 and our variable x, and determine if those are the opposite sides, adjacent sides, or the hypotenuse for this triangle with respect to our 45-degree angle for theta here. The 18-degree angle that's there, that's straight across from the right angle, so that's our hypotenuse. And then our value here for x, that's straight across from the 45-degree angle theta, so this is our opposite side. So what I want to do next is think about our acronym SOHCAHTOA. And what I want to do is take a look at the triangle that's given. We know that the hypotenuse is 18 and we're trying to find the opposite side. So that's an H and an O. What I want to do is look at the last 2 letters, which represent the sides, and see out of our 3 different trig functions here, which one is ending with an H and an O. And if I look at that, that's the first one. So sine is opposite over hypotenuse, so the sine equation is the one I want to use. So for this problem, the sine of our angle theta, but I know theta is 45 degrees, so I'm going to plug that in. The sine of our angle theta, or the sine of 45 degrees, is the opposite side, which is x, over the hypotenuse, which is 18. Once you get that set up, then you want to take a look at this table and remind yourself that we have 9 trigonometric functions here with a 30, a 60, or a 45-degree angle that we know the exact values of. And in your problem, there's going to be one of those. In this case, we know that the sine of 45 degrees is equal to x over 18, and the sine of a 45-degree angle is the square root of 2 over 2. So in place of the sine of 45 degrees here in my equation, I'm going to rewrite that as the square root of 2 over 2. And now I have an equation in it that only has our variable x, so I should be able to solve for x. On the right side of the equal sign, I have x over 18, x divided by 18. To undo that and get the x by itself, I would want to multiply both sides by 18. That would give me 18 times the square root of 2 over 2 is equal to x. And we have a regular number 18 on the top and a regular number 2 on the bottom, and that can be reduced. That just gives us the number 9. So this will reduce down to a 9 times the square root of 2. So that is how long our value is for x. Now you can do that work without going through and using trig functions. We've practiced that before. But in the directions it says use a trigonometric function to find the value of x. So you're going to want to set that up with a trig function. It's going to have either sine or cosine or tangent of either a 30, 60, or 45 degree angle, and then you're going to substitute in to find the exact value. We'll do one more of those. So here we go. We have our right triangle. Our angle 30 here is our angle theta. I know that's a 30, 60, 90 triangle, and we have some ratios for that we can use. Compared to our angle theta here, straight across from that is 12. That is our opposite side. And x this time, that is the adjacent side. So I want to take a look at O and A and figure out what trig function goes with O and A. If I look at the last two letters, there we go. If I look at those last two letters, O and A go with tangent. So this is going to be a tangent equation this time. So my equation is that the tangent of our angle, theta, that's equal to opposite over adjacent. So there's the equation that we can use with a trigonometric function to find our value for x. Tangent of 30 degrees, that's one of the values that we know. So the tangent of a 30-degree angle is the square root of 3 over 3. So I can replace that in my equation. And then from there we would want to simplify that. It is a proportion, so you could cross multiply and divide if you want to do that quickly. Otherwise, what a lot of people will do is they will take a look at the x. It's in the bottom part of a fraction, so to get the x out of the bottom, they would multiply both sides by x. That would give you the square root of 3 over 3 times x is equal to 12. And then get the x by itself by doing one of two things. One is a good idea, the other is a better idea. We have the number times x, so you could divide both sides by that number, but in doing so you would be dividing by a fraction. And dividing by a fraction is the same thing as multiplying by its reciprocal. So a better option here would be for us to multiply both sides by the reciprocal of the number that's being multiplied by x. So I'm going to multiply both sides by 3 over the square root of 3. On the left side, everything cancels out there except for the x. And on the right side, we would have 12 times 3 on the top and a square root of 3 on the bottom. That's decent, but it's not rationalized. So I should multiply the top and the bottom by the square root of 3 to rationalize that fraction. That's going to give me 36 times the square root of 3 over 3. And we have a regular number 36 and a regular number 3 in our fraction that can be reduced. So x would be equal to 36 over 3, which is 12, times the square root of 3. That is the length of that missing side. Again, you can do this a lot faster knowing your ratios. You just multiply the short side by the square root of 3 to get the adjacent, but the directions said we needed to use a trigonometric function in order to find the value of x. You do need to set this up using a trig function.